Good afternoon, this is Schweitzer, and we're going to do a little video here on a worksheet called, they're calling it the chase. All right, so this is looking at a situation where we have a truck, and you should have already looked at this thing and have an idea on it, but I'm going to add in some other information and maybe even an alternate question. So in this situation, we've done this in class, or we call this an overtake problem. There we go. And we look at something in class a little bit more mathematical and see, okay, what time does one object catch another object, or where are they, on a line, on a crooked line, where are they at the same location? When do they have the same xt mathematically? And it's just a good application of kinematics mathematically, right? So with that being said, they want us to do some stuff here graphically, which is great. All right, so first thing it says is they want you to sort of mark out a good scale here. I'm going to go 10, 20, 30, and then 40. And then here 10, 20, 30, and then 40. Okay. And then they want you to mark out the truck. The truck's just zipping along at a pretty constant speed of 20. Let's give it a different color here. And let's just kind of run this thing horizontally at 20. Okay. So this is going to be in velocity, and this is going to be time. Okay. And then at this point, the cop, what's the cop doing? Let's put the cop like in red. The cop sits there for 5 seconds. They start accelerating at 2 meters per second. Now, that means as time goes along, his velocity is increasing. Now, this is a velocity time graph, which is the slope of this particular graph. What is it? Let's remind ourselves. It's meters per second divided by seconds is meters per second squared. So the slope is the acceleration. So the slope is 2. So over 5 seconds, so the velocity is equal to acceleration times time. So that's going to be 2 times 5 is just 10. So every second I gain 5. Every second I gain 2 more meters per second. So over the course of 5 seconds, we get to here. And then another 5 seconds, we're to here. And another 5 seconds, we're to here. Now, this is just velocity. So I'm just going to draw this up here. Okay. All right. I think that it's pretty decent here. So using the graph you made in part A, determine the time. It looks like this is the time where the velocities are equal. Okay. How would the positions of the car compare at this point? Now keep in mind, it's just checking velocities, and we should note that the truck, let me get myself a little different. There we go. And the truck, you should be aware, is still in front of the car. And you could rationalize this in a couple different ways. One would just be via velocity. The truck was behind, the truck was ahead to begin with, and the velocity never exceeded the car. The velocity of never exceeded the truck. And you could word this. I'm going quickly here, so you could do your own better wording. So the cop car essentially, its velocities never exceed the truck, and since it was behind to begin with, it's never going to require enough distance to catch up. Or you could say that the cop must have had a greater velocity than the truck at some point to catch up, to make up the ground it was when it left here. And it has all the first 15 seconds, it always has a lower velocity the whole time. So it needs a higher velocity to acquire this. And the next thing you could have here would be, I would think area under the curve. Okay, area under the curve. Okay, that represents, just so you're aware, is equaling the distance traveled. Okay. So in this situation, how much actual distance is being done here? So it says here, explain in short sentence how you could use the graph you made in part A, determine the time it took for the truck to be at the same location. So let's just go ahead and check it out here, first of all, okay, for this guy. So let's take a little side note here and say, what are those distances here? So for the truck, we could say, okay, I have 20 times 15. So 20 times, remember, area in the curve is where you're multiplying together. And 20 times 15 is going to be, 20 times 15 is going to be 300. Okay, so the truck is traveled 300 meters. But the cop, now we're going to go, remember the area is relative to here. So he's not acquiring any distance in the first 5 seconds, just right here. Okay. Now you could do a visual inspection of area under the curve as a way of just describing who's ahead, who's behind, but this is more mathematical. So it's going to be 5, 10 times 20. That's for that square, but let's go 1/2 of that so we get the triangle. And at that point, 10 times 20 is 200, and 200 divided by half is 100. So this guy, cop guy, is still at this point 200 meters behind. Okay, so this elaborates this guy, and really you could calculate the area. Calculate the area. It's not as efficient because you kind of have to do just sort of check a certain time to see who in fact is ahead. So the graph goes to 40 seconds. So let's do a side calculation here. Is the guy caught, okay, at 40 seconds? So take a moment. It's not on here. 40 seconds. How would we do that? All right, well, the truck is pretty simple at 40. And at that point, my horizontal is 40, and my vertical is still 20. So we could just solve that out and say, okay, 20 times 40, and the last one was 15, so we've gone quite a bit farther. 20 times 40 is 800. Okay, so the truck has gone 800 at this point. All right. Now, what about the cop? Okay, he still, I'm assuming, continues to accelerate. I guess that's really what we're looking here. Can a car continue to go faster and faster? We'll just leave it like that. Okay. So at this point, 5 has been sitting still, and then he's going to go for another 35 seconds here. Okay, 35, and then it's going up here. So he's 2. Remember, velocity is going to be equal to acceleration times time. So 2 times, he accelerates for 35 seconds. So he's really picking up speed here. 2 times 35 is 70. Okay, so 70 is located here. And I want half of that, right? So that my 5 should have been right here. All right, it should be right here. All right, so it's going to be 1/2 times 35 times 70. Has he caught him up yet? All right, 0.5 times 35 times 70 is 1190. So the answer for this particular side question would be correct. Yes, he has. And if he didn't stop, then he'd be well past him. So let's go to the next question. Let's go next slide here. It says, okay, so position time graph. So it's actual location. So a couple things here. It says Angela and Blake are discussing Carlos's graph, the position time graph of the car. Okay. read these below. Which aspects, if any, are correct? Support with evidence. Okay, so Angela says since the cop car is accelerating, the graph of position time graph should be a curve, showing that the speed is changing. The graph of the speed versus time of this car is correct. Now, Blake says, I don't see how it can be. The police car waited 5 seconds and moving. The graph should start at 00, but 50. Okay. So, all right. So everything here is correct. Really, that this thing should be flat because he hasn't changed. Then start to curve up. So she's correct, except she forgot the part that Blake mentioned. Okay. So it is going to be curved. Remember, the slope at this point is representing the meters per second velocity, meters divided by time. So, which aspects of Angela was correct? The fact that it should be a curve and the velocity is changing. Velocity is changing. And what is correct about this guy? All of it. Okay, it should be flat. He doesn't go on to explain anything else, but flat for the first 5 seconds. Okay. And actually, it'd be flat all the way out to here, and then it would start to curve up like that. Nice. All right, thank you very much.